Welcome to this session. So basically the goal is to present you a few basic facts about Percona XtraDB cluster so that you can know whether it's a good fit for your application, what it can be used for, what are the limitations, the main features, etc. So let's start with what we have traditionally, which is master-slave. So when we use MySQL, what we have is a master where you have all the writes, and then with replication, you can send all these writes to one, to any number of servers, which are the slaves. However, this is a very great approach because it can solve a lot of issues. However, it's not perfect. One thing that we can often experience with a traditional master-slave setup is replication lag. So you have your master that can handle a lot of writes, and unfortunately, from time to time, the slave is not able to keep up with the load, and that can be problematic because if your application is not aware of that, you can, for instance, insert something on your master, then right after read on the slave, and the data is not there yet, so it's going to have some. It's going to create some problem inside the application. Another difficult thing is failover. Failover can be difficult, like if you have one master and 5 slaves, because if the master fails, okay, it's quite easy to say, well, out of the 5 slaves, let's take this one, and that will be the new master. However, when you have that new master, the difficult part is to reconfigure replication, so to make sure that all the 4 other slaves replicate from the new master. That is difficult because, and so for both issues, everything comes from how the MySQL replication works. Basically, it's asynchronous. So when you execute something on the master, you never really know when it will be executed on the slaves. And you can have one slave that is up to date, able to keep up with the load, and another one which is lagging behind. You have no guarantees about when data will be there on the slaves. And the second thing is replication is single-threaded, which means that on the master, you can commit in parallel. You can have 5 threads, 10 threads, 30 threads writing and committing in parallel. Well, on the slaves, only one thread. So that's why sometimes you have replication lag, simply because one thread is not able to run as many queries, as many commits as multiple threads. So another option is Percona XtraDB cluster. So Percona XtraDB cluster has a lot of great features. First one, no replication lag. Good, because replication lag, as I mentioned earlier, can create a lot of issues in your application. And that comes from the type of replication that is used in PXC, which is synchronous and with parallel appliers. PXC is also a true multi-master solution. So with the traditional master-slave replication, you can set up a master-master, let's say, cluster, and you can write on both masters. But this is supported, but you shouldn't do that because, well, it's the best way to have data corruption, replication errors, and any possible problem. With PXC, you can do that. It's supported. You have write conflict detection. That's great. Failover, oh, that's easy. You have failover with no downtime. Actually, with PXC, you have no failover because all nodes are equal. So if a node goes down, well, you simply ignore it and route the traffic to the other nodes. You're done. So no failover. So, well, that's great. You have automatic provisioning. That means you have a cluster with a few nodes, you want to add one, so just it's only a matter of telling the new node that it should connect to the cluster, and then the other members will send the data it needs. And it's automatic. It's mostly transparent to the application, which means that for the application, it will act as if it's sending queries to a regular MySQL server. So basically, you don't have to do any application change to use PXC. Okay, so what is PXC? So essentially, that's a regular Percona server, so quite close to a regular MySQL server, plus the Galera replication library. And the main difference between a regular Percona server and PXC is Galera. Galera does maybe not all the magic, but most of the magic, right? And the thing to understand is that as we are using the Galera replication library, we don't use the native MySQL replication anymore. Okay, so that's the main difference. Instead of the native MySQL replication, we will use Galera replication, and Galera replication will provide all that I mentioned before: the automatic provisioning, not automatic provisioning, but synchronous replication, and so on and so forth. Okay, so let's recap. With PXC, you can write everywhere, right? So here you have 3 nodes, and it's not one master and 2 slaves. It's potentially, so it can be, but it can also be 3 masters. So you can write here on node 1 and read on node 3, write on node 2, read on node 1. You can do whatever you like, okay? And you can write synchronously. So this is very interesting. You have parallel replication. So here you only have 2 servers. You write with several threads on one node, and you can also have multiple threads applying the events on the remote nodes. So that's pretty interesting to avoid replication lag. Now, regarding high availability, I will focus a bit on that because we have many people using PXC to bring high availability to their database layer. So, like I said before, if you have PXC, let's say you have 3 nodes, 1 node goes down, that's not an issue. You simply route the traffic to another node, and this works. And why does this work? Because basically all nodes are equal. So you don't have to think, okay, as all events from replication being received by the other nodes, is there any replication lag, etc. No, you don't have to care about that. Also, multi-node writing is allowed. So this means that, if you have a node that is behaving weirdly, you can simply, what you can do is, continue routing some traffic to it because, you don't know if it's going to really go down or not. And you can, at the same time, route some other traffic to another node. That's not an issue. You can do multiple node writing. With, say you have a regular master setup with a traditional MySQL application, you should avoid that. It's really critical because, again, in a traditional master setup, if you write to both servers, that's not good. You'll be creating problems. Okay, so I talked about one failure. So now what about multiple failures? So let's say we have 3 nodes. We have a cluster with 3 nodes. What happens when nodes go down simultaneously? So if we have one node that goes down, we still have 2 other nodes that remain available, and that's great. The cluster will keep on processing queries. Now let's say that another node goes down. You have another crash. So this time you only have one node that is up. The thing to know and to remember is that in this case, the remaining node will stop processing reads and writes. So it's still up, but it won't accept queries. Okay, so that can be confusing because if you think about the regular master-slave setup, okay, you have 1 slave that crashes, 2 slaves that crash, 3 slaves, that doesn't have any impact on the master, right? On the Galera cluster, when you have a crash on somewhere in the cluster, that can have an impact everywhere on the cluster, right? So that's important to remember. And why do you have this behavior? It's because of quorum. So let's talk about quorum. So to be able to process queries, mainly writes, but yeah, let's say in general queries. The nodes that you have in a cluster need to have the majority of the votes. So by default, one node equals one vote, right? So if one node disappears, what do we have? So we have 2 nodes out of 3. That's 2/3 of the votes. That's the majority. That's quorum. The remaining nodes can go on. Now, if a second node disappears, so we had 2 nodes and one disappears, 1 node out of 2, that's not a strict majority. That's only 50%. We need 51. So this time we don't have quorum. And if we don't have quorum, so if the remaining node or nodes don't have quorum, they stop. So they don't stop. They're still up, but they won't process queries anymore. And what you'll see in such a case is, okay, let's try to run a simple select, and then, wow, you have that error and non-command. Okay, so that means the MySQL server, the PXC server is still up, but because it doesn't have quorum, it says, well, I can't do what you're asking me to do, right? So this is probably a bit confusing if you're not used to it, right? Okay, so now let's try to understand that fully. So what I've just told you is that I have a node. So okay, I had 3 nodes. Now I'm down to 1 node. It's still up. It's working correctly, so there's no issue. However, I can't do anything with it. How come? So the reason is that for the remaining node, it doesn't know the exact situation. So there are basically 2 cases. The first case is, okay, we have 1 node. We only have 1 node now because the 2 other nodes are really down. They have crashed. They're down. So we could proceed in theory, right? The other option is there's a network partition. So the remaining node doesn't see the other nodes, but the other nodes are still up and running. And in that case, what does that mean? Well, as you can have multiple writers, you could write on the node that's alone and also on the 2 other nodes that are separated. So in that case, what does it mean? It means split brain. You have a divergent data set, right? And PXC will protect you from that issue because of quorum. So 1 node alone, not able to process queries, that can seem boring, but that's a very good thing because that protects your data. So okay, all of that is very good, but let's say we have a 3 node cluster. So I've just told you that basically you're only able to handle a single node failure, which is quite good. But sometimes you will need to be able to handle the simultaneous failure of 2 nodes. How can we do that? Well, that's quite simple. You add more nodes. Basically, with the rule of quorum, you can know how many servers you can lose and still have your cluster running. So with 3 nodes, you can lose up to 1 node, because if you lose 1 node, you have 2 votes out of 3, 66% quorum. 1 node out of 3, 33%, well, doesn't work, okay? So now if you have 5 nodes, if you lose 2, you still have 3 out of 5. That's quorum. Perfect, that works. If you would need to have more, to be able to handle gracefully more simultaneous failures, you would need more nodes. However, keep in mind that PXC works with group communication. It has some overhead. And if you have 3 nodes, that's okay. If you have 5 nodes, that's okay. If you have 25 nodes, that's probably not okay, right? So it probably doesn't make sense to go further than, let's say, I don't know, 7 or 9 nodes. Typical deployments are 3 nodes, 5 nodes, but 3 is really the standard. So if you think about a setup with 7 nodes, that could be right. If you think about a setup with, again, 25 nodes, well, you should probably talk to us before doing that, because that's probably wrong somewhere, okay? So a few main limitations or feature of PXC. The first one is use InnoDB. Galera relies on the storage engine to be transactional. So InnoDB is transactional, that works. My ISAM is not transactional, so that doesn't work. Actually, that's not exactly true. You have my ISAM support. It's experimental. It will always be experimental because, again, my ISAM is not transactional. So if you want to move to PXC, first thing, remove or convert all my ISAM tables to InnoDB. That's a good advice. Next thing, all tables should have a primary key because Galera replication is based on row-based replication. And if you don't use primary keys, performance will suck, to be honest. Second thing that can be a bit, well, also that can look weird is the optimistic locking that is used by PXC. We'll see that right after. Actually, it's quite interesting because it's quite good for performance. However, it can have surprising effects. Another surprising thing is that you have a replication feedback mechanism that is called flow control. And it's causing a lot of issues for users that are not familiar to it. So we'll talk about it also. And the other thing to keep in mind is that PXC does not play well with all workloads. So Peter will talk about that later in the presentation. Usually it's quite good to try to first evaluate if your workload is a good fit for PXC. If you don't do that, it can be risky to migrate to PXC, right? Okay, so let's talk about locking. First, pessimistic locking. Pessimistic locking is what you can find on, for instance, a single server using InnoDB. So let's say on the left you have one transaction. So you begin a transaction, you want to update one record. And at the same time, you have another transaction that will try to update the same record. What's going to happen? The second transaction has started after the first one and is trying to update the same record. Well, this session has set a lock on that record. So the second session has to wait. And it has to wait until the first one commits. Right? So that is pessimistic locking. Now, if you have Galera, you will have optimistic locking. So this time we have two PXC nodes. Starting a transaction on the server number 1, trying to update a record. And on server number 2, I'm also starting a transaction, trying to update the same record. This time, it works. So both will update together the same record. However, at commit time, Galera will see that we can have a conflict, a write conflict, because both sessions are trying to update the same record. So what's going to happen is that one of the two sessions will win. So it will actually commit. And so let's say that transaction number 1 commits, then when this one will try to commit, the commit will be rejected. Okay? And why will it be rejected? It will be rejected by Galera. Galera will say, it's not safe to proceed, so I'm going to roll back this transaction. Okay? And why do we have optimistic locking? Because if we had pessimistic locking, basically, when we started this transaction, we would have set a lock here, but we don't set a lock. So when we start the transaction here, we set a lock locally on the record, but not remotely on other nodes. So that's why it's called optimistic locking. And so in the event of a transaction rejected by with a write conflict, you will see a message like this saying, "Oh, you have a deadlock." So be aware that it's not a deadlock like an InnoDB deadlock. It's not the same thing. So it's simply that it simply means replication conflict. So don't be confused with a real deadlock. It's not the same thing. Okay, so I mentioned earlier the replication feedback mechanism, flow control. So what is flow control? So let's say that you have one node that is slowed down for some reason. It could be, well, you're running a backup. It could be you're running a long-running transaction that is using all the IOPS you have. It can be anything. So in this case, the slow node will tell the others that it's getting slow, right? And in this case, what the overnodes will do is they will stop processing writes. Okay, so this process of sending messages and of the overnodes pausing for some time is called flow control. And how will it appear to the application? Well, simply it will be a write stall. So when let's say node 1 sends flow control messages to node 2 and node 3, actually node 2 and node 3 will stop processing writes for some time. So the application will see that the cluster as a whole is not processing writes anymore. Okay, so that can be quite confusing. You have, again, think about that. You have one node that is slow. It has an impact on every node. Okay, so very different from master-slave, where a slow slave will never have an impact on the master, right? So a few more details about flow control. Flow control appears when you have the receive queue of one node that grows too large. So again, Peter will get into the details of how replication works with Galera. But to make it, just to give you an overview, basically, when a node commits a transaction, the transaction will go to a receive queue for the remote nodes, and then the receive queue. So the events in the receive queue will be executed. And if we put more events in the receive queue that we are able to empty, it's going to grow and grow and grow and grow. And at some point, the node will say, okay, it's growing too large, so I'm sending flow control messages. And then the other nodes will stop accessing write, so that the slow node will be able to empty its receive queue. The good thing is that this is tunable, so you have the option here. And the other good thing to know is that the default is 16, which basically means that if a node is 16 transactions behind, it will store writes for the whole cluster. And if you think about it, 16 transactions is really, 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 really low. So it can mean that if a node is like 5 milliseconds or even less, 5 milliseconds behind, it will stall all the writes everywhere. So could be good to raise that limit. So how to avoid flow control? You have more different ways to do that. The first thing is to make sure that you're using the same hardware and same software configuration everywhere. So again, with PXC, all nodes are equal. So there's no good reason why you should have a node that is slower than the others, or one node that should be better or more powerful than the others. You should have everything equal everywhere. Now, what can trigger flow control is a heavy job, like a backup. So in this case, if the heavy job is planned like a backup, what you can do is, before starting the backup, change the status of the node. You can set it to donor desync. And if you do that, it will never trigger flow control. So the receive queue can still, okay, thank you. The receive queue can still grow very large, but it will never trigger flow control. That can be very useful. Another thing is that you can have large reporting queries. So this time it's a bit more difficult to use the donor desync state because, well, large reporting queries can happen anytime. So in this case, a good practice could be to set up an asynchronous replica and then run the reporting query on the asynchronous replica. And the last thing is to increase the setting, so increase the threshold from which flow control is triggered, because the default is very low. And now I'm going to turn the mic over to Peter for the rest.
Okay, thanks. So, hi everyone, I'm Peter, and we will talk about how can you decide if XtraDB cluster will mean an issue to you without suffering from those issues actually. In order to do that, we will need a slow query log from Percona server with some parameters set, like log slow verbosity full. Slow query log use global control all is not strictly necessary. It can help you a lot if you have persistent connections, meaning that if a variable in MySQL has a global and a session scope, the global is just a default for new sessions. That's too bad for long query time, because if you set it to 0 to collect your workload data, then it will only affect new sessions, so you have to wait a while until it becomes relevant. If with default connection pool configurations, it can be like up to a day or 8 hours. It's a lot, but with slow query log use global control all includes long query time. It means that if you set long query time to 0, it will affect running connections as well. This is a Percona server extension. So there are really two issues we are after. One is detecting data hotspots, and the other is detecting long-running transactions. If you remember it, data hotspots, we call it data hotspots if we have a multi-node writer conflict, or on a single node we have a lock wait. With the extended slow log, we are recording the InnoDB transaction ID, and we are recording the time spent in record lock waits. I'm doing it with this because it's much more convenient, right? It's made for that. So record lock waits is here. Okay. So how do you check for the statements which are waiting for record locks? Again, why do you want to do it on a single server or on an existing system? Because if you are migrating to PXC in a multi-writer setup, these will turn into write conflicts. And why do we want to detect it so bad? Because in the case of a pessimistic lock, in a case of a lock wait, it's not the most pleasant thing in the world, but it's still a wait. Right? It doesn't consume resources. In case of a multi-node writer conflict, it's a rollback. A rollback is a very expensive operation in any kind of database engine, because everybody optimizes for the commit path, because it should be more frequent than rollback. Rollback involves copying data back from the undo area, so it involves I/O. Nobody likes stuff that involves I/O on the database server. So database kernels are working towards avoiding I/O. So we are ordering the queries of the slow query log. PT query digest is practically a slow log aggregator. So you might use it to detect the top queries, but it can use for much more. So it can aggregate the slow log based on practically any field of it, because it's a parser and the aggregator. We can order by the time spent in record lock waits. See, InnoDB rec lock wait sum. See, we have an InnoDB rec lock wait field here, so we can do this here. And if we add group by InnoDB transaction ID, then instead of statements, it will check the lock wait, the time spent in lock waits in InnoDB transactions, and this is when the sum comes into play, because a transaction can be multiple statements, because an event in the slow log is a statement. So in order to know how much time the transaction spent here, we have to sum these up. So that's the sum part right there. The other thing we are after is long-running transaction. Why is that an issue? The issue comes from how replication works. If we have parallel replication, and let's say all of these yellow bricks are 10 millisecond transactions, and we are applying them in parallel. Let's assume that we have 6 arrows here. But if we change one of them to last for 1 second, after 10 milliseconds we will have this state. And the reason why we have this state is how replication works. So whenever a write happens or a transaction happens on one node, the server processes it, signals OK, and we replicate at commit time. we replicate the write set to each of the nodes in parallel. So this is the synchronous network transport part. And the global transaction ID is established. The global transaction ID is established for group communication. So for the same transaction on all nodes, the same global transaction ID will be assigned. And then the certification happens. Certification doesn't happen before replication, but after. Certification, so let's talk about certification. Galera replicates in write sets. A write set is practically a row-based binary log event plus some metadata. The plus some metadata is good for two things. You can take a look at the write set and the database and tell if the write set is applicable to the database. And you can take a look at two write sets and tell if they are conflicting or not. At the time of certification, these two things are checked. It's checked if it's applicable to the database, and it's checked against each and every write set in the queue to detect conflicts. And this is why parallel replication is possible, by the way. We can have M threads replicating here because we know that these are not conflicting. And we know that these are not conflicting because of the certification process. You know, if it's okay, then the user will receive back an acknowledgement. Otherwise, it will receive the deadlock error. On the remote side, if it's okay, it will commit it. Otherwise, it discards it. Please note that this green part can be after the okay for the user. It's actually, if I try to make a really straight line, you know, with this pointer, it's actually, you know, part of that is after. So the point is, by default, you are not able to read your own writes, but you can configure the cluster to enforce such a strong consistency. So long-running transactions can store replication. How do we detect long-running transactions? We can check the transactions or statements with the most rows affected by ordering by the sum of rows affected. Again, we can optionally add group by InnoDB transaction ID. If you remember, here in the slow log, rows affected, here it is. It's 1, so this is not such a large transaction. We can check transactions with the the title is wrong. We can check the transactions with the most time spent in it. We can check the digest of writes only by filtering out everything which resembles a read. Okay. And so replication is synchronous. The other issue which you can have is because of synchronous replication. That means that each commit will take at least one network round trip time. Okay, so this might sound very limiting, but remember you have parallel replication on the other hand. So you can probably maintain, if you can maintain this throughput through parallelism, then it's good. We have seen workloads when this yields in slower performance than normal async replication, but we have seen many workloads when this is actually much higher performance simply because of it being parallel. Especially these days when servers with 24 cores are considered commodity. So each write set is sent to all the other members in parallel. So like Stephane said, clusters with lots of nodes can be an issue because of this. Imagine that if a write set consumes bandwidth X, if I have like 8 other nodes in the cluster, I need 8x bandwidth. Okay, you can have nodes on WAN link, but this multiplies WAN traffic. You know, WAN traffic multiplication is not the most pleasant thing in the world. So if we have such a 6-node cluster in 2 data centers, which is completely wrong, because what happens is that if this connection breaks, then none of the data centers will have quorum. Actually, it's not wrong because you most likely you set the weight of the active one higher. So the point is that if you are doing multi-data center, similarly to the machines, the magic number is always odd. Okay, so this van traffic multiplication is very undesirable. That's why group segments were introduced. By introducing group segments, you can configure it like this is group segment 1, this is group segment 2. By default, everything is in segment 1. What will happen is within segment, the old behavior is preserved. Between segments, though, each transaction will be replicated only once through a gateway node. That gateway node is chosen automatically, and it's chosen automatically on a per transaction basis. So, for this transaction it will be these two, for another transaction it will be these two, for yet another transaction it will be these two. So, it's not affected by node failure at all. So it's not affected by node failure at all. This can also be used not only for WAN links, but it can also be used to build larger clusters, even if this is not a WAN link, because this also helps, the bandwidth multiplication problem. So that's it. Do you have any questions for us? Yeah.
I've been considering using DSP. My worry is optimistic block.
Mm-hmm.
It's not going to be our application handler right now. It's not going to be coming back to that. So I'm wondering if it's a reasonable option to have an XP cluster with only one node that's read write, and the remaining cluster be read only. And if so, if that still gains me much when I'm looking mostly to get automated failover, also some UTM, but mostly to get automated failover. Is that a realistic setup?
Yes, it's quite common. You will also gain parallel replication, and so the deadlock handling. If you can get a deadlock anytime from InnoDB as well, right? Or you can get a failed. So a transaction can fail in the database. The database's job is to signal it to the application because the application knows how to handle that failure, right? So that's the thing. You have to have some logic in the application for that. But it's a fairly common setup. It's we even have in the documentation, we even have tuning recommendations for that kind of setup.